what I'm going to talk about in the mini course is kind of consequences of geometrization, particularly algorithmic and group theoretic consequences. So I'm going to start today with talking about the homeomorphism problem for three manifolds. So we just first, the convention is that all manifolds are oriented. I mean, this is not anything like a fundamental assumption. You always pass through a twofold cover to make it orientable, but it does ease the exposition a little. So what's the homeomorphism problem? So it's just given two, let's say, closed n manifolds, M and N. So are they the same? Are they homeomorphic? Well, you could also ask about diffeomorphism, but again, in dimensions 2 and 3, there's no difference between these things, thankfully. And you know, what do I mean by given here? I'm really thinking, you know, this is supposed to be like a computational algorithmic question. So given is going to mean, for example, as simplicial complexes. So somebody hands you a finite bunch of tetrahedra glued together, two of them, asks you, are they the same? Are they the same manifold? The question I want to talk about today is there a computer algorithm? The usual terminology is this homeomorphism problem decidable? Right. So Ian mentioned some problems that are not decidable, like it's not decidable whether a finitely presented group is the trivial group. So in particular, that means you can't decide if two finitely presented groups are the same. You can't even tell if one of them is trivial. So in this context, whether or not the homeomorphism problem is decidable has an algorithm that depends on the dimension. So in n equals 1, so it's going to be decidable. And in fact, I can describe the algorithm. Right? There's only one closed one manifold. So that's the whole program. All right. Well, two manifold surfaces, we have this beautiful classification of surfaces, right? Any orientable surface is just a connected sum of tori. And so that's concrete enough that I can also write down the algorithm, which is the output, whether the Euler characteristic of M is equal to the Euler characteristic of N. And if I'm thinking of my input as simplicial complexes, right, this is very concrete to compute. Just count the number of cells and add them up appropriately. In higher dimensions, the answer is no. This was shown by Markov in the 50s. And, well, you might remember from this morning that in dimensions 4 and more, any finitely presented group is the fundamental group of a smooth closed n manifold. So in some sense, we should expect questions about manifolds to be at least as hard as questions about finitely presented groups. And as Ian said, some of those questions, even very basic ones, like is the group the trivial group or not, those are undecidable. So it's not so surprising you can leverage that to say that, yeah, manifolds are also undecidable. So for n equals 3, the answer is again yes. But in this case, it's not near, I won't be able to write out the whole program. And like so much of three-dimensional topology, it's a consequence of the geometrization theorem. So this is a corollary of geometrization. This was sort of widely believed to be the case, that it followed from geometrization, but no one actually proved it until Kuperberg actually wrote out the proof, or a proof. And it's non-trivial. That there's an algorithm? Okay. There's a second proof. In any event, it's the case that the source of this, the reason this is yes, is going to come from geometrization. Without geometrization, you have, to best of our understanding, no way of approaching this question. Is there any? Yes. So yeah. So it's at worst. So I think it's primitively recursive. So it's at worst like a tower of exponentials of fixed height. Okay, so that's not great from the point of view of doing things. That's a really good question because that comes back to my distinction I'm going to make. So in the first part of talk, I'm going to talk about the theory. And in the second part, I'm going to talk about in practice. And in practice is, in theory and practice are the same. In practice, they're different. And this is one of those cases. So it will turn out in practice, I will on my computer there, I will solve the homeomorphism problem in real time for complicated manifolds. Okay, so in practice, this is practical. But in theory, it's hard. And there's lots of things about computation in three manifolds that are of this form. So, there's a statement that an algorithm exists. The algorithm is, in this case, unimplementable. But despite that, in practice, you can do it anyway. And make of that what you will. Okay, so let me talk a little bit about this, the algorithm, which really, or why. Basically, I just want to say, why does geometrization help? Okay, what is the input there? So, kind of the broadest outline. How do you understand this? So, the first is we have to find. There's a decomposition here, right, in the statement of the geometrization theorem. So the first step is to find the geometric decomposition. So this is the JSJ decomposition, which is a purely topological thing. It was in fact done prior to the proof of geometrization. And well, there'll be, as I emphasized before, there's the sort of hyperbolic geometry, and then there's the others. The other pieces, the manifolds, they're called cipher-fibered typically. I'll give examples. They're sort of completely classified topologically. It's not like the classification for surfaces. It's not just output Euler characteristics are equal, but it's not. They're very, relatively speaking, simple. So then, let's just say the non-hyperbolic pieces are classified. And for the hyperbolic pieces, we rely on Mostow rigidity. Right, so Mostow rigidity said if you had a hyperbolic metric on a manifold, there's only one of them. Right, any two hyperbolic metrics on the same manifold are isometric. So use Mostow to reduce the homeomorphism problem to an isometry problem. I'm trying to check if these two manifolds are the same. I just need to check if they're down to, by this stage, checking the hyperbolic pieces are the same. Then that hyperbolic, checking that, I can actually just check if they're isometric. And that's a very rigid, isometries are rigid things, as I'll explain. And so that turns out to be a lot of leverage. Oh, yeah, right. So unfairly to Prasad, the case of finite volume, Mostow's theorem is due to Prasad. So it's not really Mostow-Prasad rigidity. Okay, so I just want to talk then a little bit about some of these concepts here. So what are these sort of simple manifolds? These came up in Ian's talk. So a three manifold is cipher-fibered. When it is foliated by circles. So we've divided the manifold, partitioned the manifold into a bunch of circles, which locally, on a small scale, they just look like a little stack of spaghetti. So we need examples. So the basic example would be take a surface across a circle, right? Because then we can foliate this by points cross circle. We could do something slightly more complicated. We could take the unit tangent bundle to a surface. So pick any Riemannian metric on a surface. We look at its tangent bundle. We can look in that in the tangent plane. Right, we have a circle, unit vectors. So that's actually a 3-manifold, right? And this is well, the way I defined it, this again has this foliation by circles. And these aren't the only examples. Another example is, say, the 3-sphere. This comes from the Hop vibration. You remember algebraic topology class. And if you're not familiar with this is on the homework. And so, you know, other things, lens spaces, 3 torus. Well, I guess that's an example of this. There's lots of examples like this. And why are these sort of pleasant things to deal with? Well, to reduce the dimension. So, so if I have a cipher fiber manifold, and it's an infinite fundamental group, or something like the 3-sphere, then it's even simpler than one of that. Then so finite cover. This finite cover with 3 and then the structure. Well, that is very obvious. It's non-trivial finite cover. That's fundamental. So it's in a exact sequence. This is the surface. So 3-manifold. This is pi of the these other hypercircles. After passing through a finite cover, any cipher fiber space are actually upon the over the symbols. It is really just something like this. And consequently, in theory of fiber bonding, it's obviously the fundamental group of your manifold. Looks like fundamental group of the base. We have this sort of exact sequence, the fundamental group of the base. And since I know a lot about surfaces, okay. And this extension here, this thing is central. It commutes with everything in the. So this is a quite special structure, which again kind of allows us to reduce the dimension. I believe Danny will be telling us something about this in his series. So these, except for H3 and solve, manifolds with other 6 geometries, they're all cipher fibered. And the cipher fibered structure itself is rich enough that, in fact, usually you don't have to think about those geometries. You just think about them as cipher fibered and purely topological. So if you're worried that you don't have to master like these 8 geometries, it's really mostly a story of hyperbolic geometry and cipher fibered spaces. So, but maybe, part of this geometrization theorem is, which I didn't write, I guess, is that this decomposition is unique. And so maybe I should justify, so I've said so little about hyperbolic 3 manifolds, maybe I should justify why a no manifold of this form is a hyperbolic manifold. All right, that's a very natural question. I describe these manifolds. I keep saying hyperbolic manifolds, yay, they're everywhere. Why aren't these hyperbolic manifolds? So maybe I'll do that. Proposition, no cipher fibered space. Just to be concrete here, let's think we're thinking about closed. The point is that, so here was our story for cipher fibered things. Right, for hyperbolic things, as I mentioned, we can think of the fundamental group of your hyperbolic manifold as a group of isometries of hyperbolic space, which I insisted was just a subgroup of 2x2 matrices, a PSL2C. And so, here, right, we have this group has a large center. It has this element here that commutes with everything in the group. But if we look at, say, this group of matrices, the center of this group is what? I'm sure someone in the room knows. It's the identity, right? 2x2 matrices, they're not, sometimes there's only 2x2, but they hate commuting, right? Two matrices only commute if they're simultaneously diagonalizable, basically. So, the center of this, so if I have a subgroup of this, and it's not, not the whole thing to be sure, but it's a pretty big thing, then if you had something commuted with every element of this big group, that element is basically going to have to be the center of this. So it has to be the trivial element. So let me write this out as another proposition. So if I have a closed hyperbolic 3-manifold, then its fundamental group does not contain the group Z squared. That's my claim. And once I've shown this, this is really just a corollary, right? Because take any other element in this group besides the center, those together generate a Z squared, right? So if you're coming at this workshop from like the perspective of geometric group theory, hyperbolic groups, well known not to contain Z squared. In some sense, this is really the most simplest case of that. Other questions? I know we're kind of in the after lunch dead spot. Y'all are much quieter than in the morning. Right, so I haven't proved the proposition yet. That's what you're asking. So the point is, what I'm trying to say here is that this group has no center. This group is a pretty big subgroup. Therefore, you should find it plausible that it has no center. And if that's right, and I'm going to prove that here, if that's right, then it can't be Seifert fibered. Because here you do have a non-trivial center. Yes. I mean, central extension by Z. Yes, that's right.
Then after talking to find cover, you'll get this.
Oh, so I was interpreting the questions I was given this information here. Right, so I'm saying Seifert fiber means you pass to a finite cover and you get this. But if you just give me this, then I think you are actually a circle bundle. This is, this short exact sequence, you can immediately, you can immediately, but you can turn this thing into a circle bundle over the base. Right, just Seifert fiber. It is, because you take a finite cover of a Seifert fiber space, the vibration pulls back. And really, for those of you who know that really the general thing, the reason I'm passing to a finite cover is this really should be a two-dimensional orbifold. And if I allowed myself orbifolds, then this is kind of, yes, I think that would be correct. Yeah, other questions? Sure. Yeah, absolutely. What's an example of a Seifert fiber space whose fundamental group is Z? S2 cross S1. Yes, absolutely. That can't be hyperbolic. Yeah, so you're right. That proof doesn't apply. But I proved last time that S2 cross S1 is not hyperbolic, right? Because its universal cover is S2 cross R, which is not R3. So yeah, that's right. So the fact that it's not hyperbolic, there's a special case for Z, which we thankfully already did. All right. All right, so I wanted to prove the proposition. Okay, so I really talked very little about hyperbolic space in detail. I haven't talked about it in detail at all. So let me tell you at least some fact about it. A consequence of negative curvature is that we have an isometry of hyperbolic space. We can look at the set of points which are moved the least. And with the Euclidean translation, that's every point, right? With the Euclidean translation, every point is moved the same amount. But in hyperbolic space, there's actually an axis, a set of points. This is a geodesic, which is moved the least. And if you're farther away from that, you're moved more. Because so hyperbolic geometry means things expand rapidly as you move away from where you are. So, so any element of pi1 of m acts as a hyperbolic isometry, sometimes called loxodromic, but anyway, element with a unique axis. Here's our axis. And so in particular, like what the map looks like on the sphere at infinity is, say, stuff is being pushed away from this point towards this point. So if you're familiar with the upper half space model, you're not, I'm just mumbling. This is a map like sort of on the boundary z goes to 2z. Something like that is expanding everything away from this, pushing everything towards infinity, and translating up along the axis. If we had two elements, these guys generate some free abelian subgroup, then, well, because they commute, so I have this element is acting on the sphere at infinity, and there are two fixed points. If I have something which commutes with it, it has to preserve, possibly interchange, but preserve those two fixed points. So they commute, then sort of the fixed set of alpha is preserved by beta and conversely. Which is to say that the axes of alpha and beta have to agree. And so both alpha and beta are translating along this axis. And you might think, well, so what? I mean, it's easy to make z squared act on the line, right? Just take translation by 1 and translation by square root of 2. Right? That gives you a nice z squared sitting inside of R. But the thing is that that group would not be discrete. So the point now is that this implies, because the group is discrete, because if they were irrationally related, then you could take a point and move it arbitrarily small distance, and that would violate sort of the properly discontinuousness. Since it's discrete, this implies that alpha and beta are part of the same cyclic subgroup. And in particular, they don't in fact generate a z. So the point is that what this is really saying is, if I'm in a closed hyperbolic three manifold, any two elements commute, they actually are part of the same cyclic subgroup. Which is also like the case for free groups, if you think about it, right? Yes, absolutely. Oh, well, so there won't be any elements of finite order because a finite order isometry of hyperbolic space always has a fixed point. And this is like the action of covering transformation. So all the elements are acting freely. But no, I'm not using it as z squared. Really what I should have said is that any two commuting, any two alpha and beta that commute, they generate the same cyclic subgroup. Was there another question? Okay, so we have these Seifert fiber pieces, and I explained how those had to be different than the hyperbolic pieces. And in fact, the hardest part of geometrization is essentially kind of the converse of this thing here. So part of geometrization, I should say, one consequence of geometrization is the Poincare conjecture that Ian mentioned, and deriving that actually is one of the exercises for today's lecture. And not to sort of denigrate the Poincare conjecture, but its proof is easier than this. So geometrization's hardest part is that if you have a closed, irreducible free manifold with infinite pi1 and no z squared in pi1 of m, that this implies hyperbolic. So really, this is effectively a purely group theoretic characterization of the hyperbolic three manifolds, right? Because irreducible is the same as not being freely decomposable in the end. So this is telling us these are the hyperbolic manifolds. So Perelman proved both geometrization and the Poincare conjecture. I put Poincare conjecture on the way to geometrization. Geometrization is a stronger statement. So directly from this statement, you can derive the fact that the three sphere is the only simply connected three manifold. Well, Perelman proved them basically both at the same time. It took longer for the community to understand his proof of the full geometrization, because there's a shortcut that you get to use to just, quote unquote, prove the Poincare conjecture. But they're really kind of one piece, both using the same technique. Okay, so all right, so I wanted to say just a little bit about this decomposition, and then I'm going to hint at why this lets you solve the homeomorphism problem, and then I'm going to show you how you solve the homeomorphism problem in practice. Or rather, I'm going to solve the homeomorphism problem in practice, but I'm not going to explain how I'm doing it. That'll have to wait for the second lecture. So, right, so remember we talked about incompressible. So this just meant that the fundamental group of the torus injects into the fundamental group of the manifold. So a three manifold, just need a definition, atoroidal, if every incompressible torus is parallel. Now let's put it, what do I want to say, homotopic. Let's just say homotopic into the boundary of the manifold. So because I in this thing I have to cut along tori, I do kind of have to be thinking about manifolds with torus boundary. I can't just stick to the closed case. So in particular, I think like the exterior of a knot. We saw those, and those are hyperbolic, and they do have z-squareds that come from these cusp things. I'll talk about that in a minute. But if the manifold's closed, this is just saying no incompressible tori. And so the Jacob-Salen-Johansen decomposition is that so any, let's say, irreducible closed three manifold has a collection of tori. I should say and this is really important, incompressible tori. But we don't want to. If we're trying to think about understanding the fundamental group of what results, we really want always to be going on incompressible things, because that's when Seifert, Van Kampen sort of tells us like what the fundamental group is easily. Free product with amalgamation, such that all pieces are Seifert fibered or atoroidal. So the pieces just have to be cut along these tori. This is essentially, so any minimal such T is unique up to isotopy. So let me draw the cartoon. Yeah, exactly. Right, so we have some manifold. Yep, and this manifold is going to have some collection of tori in it. Then if we cut along the tori, we'll get a bunch of manifolds with torus boundary. And so maybe some of them are Seifert fibered, like maybe this one here is, maybe if I take a disk with three holes and cross it with a circle, that would give me a manifold with four torus boundary components. So that's a Seifert fibered piece. Maybe this is an atoroidal piece. So geometrization will say those atoroidal pieces have hyperbolic metrics. So maybe this is something like the three sphere minus, let's say, an open neighborhood of the figure 8 knot.
What about solved?
So we will not get a solved. So solved manifolds are very special. They're all essentially torus bundles over the circle. And in that case, technically, it's JSJ decomposition, take one of those tori and cut along it. But generally speaking, the geometric decomposition, you don't want to do that. So once you start cutting it open, you don't not to see solved geometry. So this here, I think this is an H2 cross R geometry piece, for example. And then maybe some of these others are atoroidal. So maybe these are hyperbolic pieces in secret. Here's one that's sort of glued to itself. You imagine there's a complicated graph of how these things are stuck together. But the point is some of the pieces are cypher-fibered and some of them are hyperbolic. Yeah, thank you. So the reason you say minimal is there's lots of extra tori hiding in this thing, right? If I circle, say, these two boundary components and cross that with a circle, that's another torus. And there's another one here. And actually, there's lots more of them that are a little harder to see. Okay, so if I took like a maximal collection of these tori, I'd sort of break this piece into a bunch of subpieces, which might be fine, but maybe not if I'm solving the homeomorphism problem, because there'd be multiple ways of doing that. And so I kind of want to make these as big as possible, and that's the minimality. Yeah, thank you. Yeah, exactly. That's right. So we can maybe move these a little, but isotopic through homotopic through embeddings. Yeah, that's right. So I mean, that's right. So the atoroidal ones. So I would call these hyperbolic. Maybe I should just this is pre-geometrization. So these are all atoroidal, and then Thurston himself showed that if you have boundary and are atoroidal, then you're hyperbolic. So after the fact, we know that these pieces are hyperbolic pieces. Other questions? Okay, so now I wanted to, before I switch to the fun and games, I wanted to hint at how does this setup help us? Right, my outline was I was supposed to first start by finding these tori, finding these surfaces in three manifolds, and there one uses something called normal surface theory. So this was introduced by Haken from this vantage point in the 60s. And the idea is that, we have some triangulation of our three manifold and we're studying surfaces in it. And if I want to do anything kind of computational or combinatorial, it'd sure be nice if my surfaces looked like just a bunch of planes that kind of cut across. Right? I mean, you can only imagine I could store this picture in my computer, right? And the magic of normal surfaces is that incompressible surfaces like this, you can always isotope them to be normal. I'm not going to explain that. But in any event, there's a long theory that builds out of Haken's work that allows you to do things like find the Jacob-Shewin-Johansson decomposition. And so so there's that family of sort of purely topological tools that you use for that. So this is like sort of this is how you find the JSJ decomposition, and it also sort of helps you decide the cipher-fibered pieces. But then where the hyperbolic geometry comes from is sort of the role of geometry. Is that just much easier to find, to search for, than sort of more general homeomorphisms. Because, all right, so this is going to be a real cartoon, but you can tell I like those things. Here's my hyperbolic surface. And, it's a geometric object, so we can ask questions like, okay, what's the shortest curve? And I'm trying to decide if this thing here is homeomorphic to some other thing. Maybe I don't want to make it too obviously the same. Now, I realize these are homeomorphic, but it's the wrong dimension. Anyway, but we're trying to we're trying to see if this is homeomorphic to this. In particular, we want to either build the homeomorphism or we want to know that we can't. So knowing that we can't is the hard part, right? Building a homeomorphism is just exhibiting a map, right? These are like made of simplices or something, that transforms it into this, and you just check. The hard part is knowing that doesn't work. So over here, well, we look at this picture and where's my shortest curve? There it is. Okay. Well, if there's an isometry, it has to send this curve to this curve. Okay. If they have the same length, well, maybe we could do that. So we could say, what are the next shortest curve? Maybe it's this. And over here, maybe it's this. And well, okay. Now we could look at like the shortest arc from between these two curves, right? And maybe this is the shortest arc here. And by this method, we're either going to somehow effectively build the isometry, or we're going to get stuck. Here, we're going to get stuck at the next stage, because what's going to happen next is I pick my next longest curve, which might be this one. And then I say, okay, what's the shortest path from that to my existing curves? Well, it goes to the red curve. Here it goes to the blue curve. So we're not going to have an isometry. Other questions?
The philosophy so back the red curve is separating on the left and not on the right.
Yeah, I mean, right. So in this case, of course, I could have already said once I identified the shortest curves that they were different, because this is trivial in homology and this isn't. But I didn't want to, because this is wrong dimension, I didn't want to say that. Yes. Okay, so now we come to the fun and games. Okay, so I'm just going to demonstrate here this program called Snappy, which I'm one of the developers of, which is a tool for, yes, thank you, which is a tool for studying hyperbolic structures on three manifolds. And it's available on Mac OS, Linux, and Windows. It works essentially the same on any platform. So I have Mac, so that's what I'll show you how to use. It's easy to install. If it's not easy to install, you ask me. We fix it. So anyway, I just started the program, and you can see it's a sort of command line based thing, which is always a little intimidating because you never know what you're supposed to do. It does say here that we're supposed to type manifold with a question mark after it. So I'm going to try that. Okay, so typing question mark after something gives you the help. The help is also available on the web page. You know, there's all sorts of stuff, tutorials, bits and pieces, but it's also all available here. So I type manifold and I got this thing. So it's a triangulation with a geometric structure. Then there's some words. I don't like words. The thing to focus on is in the help, there's always examples. Okay, these are code that you could run. So all I'm seeing here, I'm supposed to, let me copy that, and I'm just going to type it in and see what happens. All right, well, I typed it in and saw what happens. That's not, didn't do anything. Let me just make this bigger so make sure everyone can see it. Okay, so we have, so that's sort of, well, so maybe I'll go back to my example. It gave me an example of something I could do to it. I could type dot volume with parentheses after it. Yes, it's giving me a volume. What does that mean? Well, again, we could ask it with the question mark. And it says returns the volume of the current solution to the hyperbolic gluing equation. So this is supposed to be, this number, supposed to be some approximation then of the hyperbolic volume, which per Mostow is a topological invariant. Now you might want to know what else can I do with this manifold? So the first key thing to know is the question mark. The other is, let me not have this be at the bottom of my screen. Is that if I hit the tab key, it says there's many possibilities. Let's just, okay. If I hit H and hit tab, this is all the things I can do with the manifold that start with H. There's homology. I recognize that. And it says the homology of this manifold is Z. Now, you're probably wondering, what is this manifold? So we just typed in a name, and that name is actually the name of a knot. If you're familiar with knots in the Rolfson table, for example. And knot exteriors do have first homology Z, so this is good. But I should just show you how to see as much of this as possible at once. Okay. So this was the browse command, which brings up this window, which has a lot of information in front of us. So here's the volume. Here's the group. I realize it's a little small. I apologize. There's a relator. So it's 2 generators, 1 relator. This is rank 2, and also Heegaard genus 2. I claim that this can solve the homeomorphism problem. And that's actually what all this information is here. So SnapP comes with hundreds of thousands of manifolds built in, and you can ask it, given your manifold, is it one of the ones that you know about? And the answer is sometimes it will say yes and sometimes no. These are all the different names that it knows about for this manifold, and it was solving the homeomorphism problem to print that. All right. So in terms of, I mentioned that we should think of hyperbolic manifolds as quotients of hyperbolic free space under a group of isometries, just like we think about the flat 2 torus as the quotient of the Euclidean plane under a z-squares of isometries. This is the square for this manifold. In other words, this polyhedron here tiles hyperbolic space, which is this sort of light gray Poincare ball that you see here. And this is the tile. There are gluings, so things of the same color are actually glued together down in the manifold. It's got this pointy thing because this is one of these non-compact ones. So I said this came from a link. This is actually the link it comes from. So it took S3 and just deleted this. So this is a manifold of finite volume, but it's not compact. So this is one way we can visualize it. Here's another way. Sorry, there's too much information here. Let me turn off some information. Absolutely. Absolutely. Let's challenge accepted, right? Is that what you're supposed to say? So let's just all right, so I'm done drawing that. So we send it to SnapP. And we ask it, okay, before I try to draw a picture, let's ask what the volume is. That's 0. Anybody recognize this? This is the unknot. Yeah, it is. Okay, this is a group theory conference. What is the group condition on the group of the exterior to be the unknot? It should be Z. Well, let's double check that. Yes. Okay. All right, but he asked for like an example. All right, let's just change some of those crossings there. I made it alternating so it goes under and over and so on. And let's send that back. And we can browse it. It failed to compute the Dirichlet domain. Oh, yeah, whatever. We just need to up the precision. So all doing, this is floating point computation so far. So we just did not give it enough digits. Here we go. It's just sort of complicated. We can also view this. So again, this is the link we started off with. We can also view this sort of looking into the manifold. So this link is drawn in red. You should think of there's a little tube around this, right? The boundary of the regular neighborhood. We're going to stand on that tube and look into the manifold. And this is what we see. Just add a few more. So I mean, so this manifold has I haven't described this very well yet. This has a cusped end. So the boundary torus is sort of a Euclidean torus, and as you go to infinity, it sort of shrinks. So I'm standing on one of those tori, and so and the torus is red. So I'm standing on a red plane. I'm looking back into my manifold, and I'm seeing these are the other copies of that red plane. And the whole thing is spinning. Oh, there we go. I was just asking it to draw more, and it was complaining. Anyway, so these are the other. There's actually copies of me on each one of these things. Many copies of me. Anyway, this is all. We can also. This is the view from inside the manifold. This one's a little complicated. Let me switch to the other one, which I'm is okay. This is the. Internally, these manifolds are stored as triangulations. So these are these horoball things, horospheres. These are the boundary tori in the universal cover. These are the edges of my tetrahedra. Maybe we'll shrink that. There we go. Shrunk that neighborhood. So these are our tetrahedra. Let me fly around. And this. So I'm not responsible, I should say, for this part. These graphics are all done by Matthias Gerner. He works at Pixar and does mathematics on the side. We talked about, I was just drawing pictures of like short curves, right? Short geodesics. Let's draw some geodesics. So this is just asking for how many, list all the closed geodesics in this manifold of length at 1.5 hyperbolic units. It turns out that there are 3 of them. I'm going to draw one of them. Okay, and let me turn that cusp back on here. Of length bounded by 1.5, exactly. So here is these geodesics. So geodesics, of course, a line, and I'm taking a little neighborhood of it. And I control the radius of the neighborhood with this slider here. So if I make the neighborhood really big, eventually it sort of bumps into itself. A little narrower. I can put in other ones. And sort of glitching over there. Okay. We need more quality. There we go. There we go. Better. These are geodesics in the manifold downstairs. So downstairs, right, I had that picture genus 2 surface, I had that little closed loop. Upstairs, that becomes a geodesic line. These are neighborhoods of that geodesic line. So each of the purple ones, they're all taken to each other. So downstairs, we'd see a single purple tube with a purple geodesic at its core and a turquoise one, and I guess the other one must be cyan. So I guess maybe
So the eggs are supposed to be neighborhoods of geometric.
yes.
They're supposed to be tori if you.
They're really like a punctured plane, right? So the geodesic we had this geodesic and we had the thing translating along it. So what you see in the picture is like a banana type thing, and that's what we're seeing here. Sorry, the geometry of. Oh, this is just we're standing in the manifold and light follows geodesics. That's right. And you could see a long way. That's the other thing, right? Yes, absolutely. Yes.
So the points of the sort of ends of those geodesics, are those on the boundary?
Yes, exactly. And those are like, so the element corresponding to the fundamental group, there's going to be an element which is translating along this banana-like thing by some amount.
So what if you try to move the camera over to the end of the geodesic?
Right. Well, so we'll never get there because it's at infinity. Yeah, I'm chasing it. I can even I think it'll let me go inside of it and then it disappears, I guess, but back up. Anyway, many of the homework problems for today are download Snappy and play with it. Because there's a lot of things that I would like to show you, and I'm out of time, so I'm going to stop. But maybe I have to do one. I'm sorry. So I should say everything I've done so far has been kind of numerics. I'll describe next lecture exactly how it's finding these hyperbolic structures. But since it came up earlier that the only knots in our experience are trefoils and maybe occasionally figure eights, I wanted to show Danny that it's not my experience. So let's take a random link, random knot with roughly 43, not in my, yeah, 43. So I just picked this. This was generated at random. This is much too big to be able to parameterize. So let's take the exterior of this thing. And so now we'll see if it's hyperbolic. Looks hyperbolic. Great. What's the volume? 72. All right. Now that's not a proof that it's hyperbolic, but it is. The computer just proved it. Well, it wasn't until I asked it to verify. And you know, by Mostow rigidity, the volume of this manifold is an invariant. And here are the first 300 decimal digits of its volume. So anyway, I'll stop there. Thank you for your attention.
There might be some questions in the chat as well. I don't know.
I'm checking right now. I don't see any questions.
Okay.
Yeah. It's a technical stuff. Oh, well, yes, in fact, I mean, Snappy is the work of many people. And we are actually not responsible for the manifold databases. So they've been compiled over many years by various groups of people, often led by Jeff Weeks, but the knot databases have been done by Morwen Thistlethwaite, Jim Hosty, Ben Burton. So those are in the literature, and we simply incorporate them. Not really. So that's the thing. But it's a little bit tricky to say because, of course, if we had a hard problem, how would we know? Like, you ask me, how do I recognize the three sphere? The answer is you hand me a triangulation and you ask me, is this the three sphere? What I do is I simplify the triangulation as much as I can. I get the presentation for the fundamental group. I simplify that as much as I can. It's a trivial group. The answer is yes. If it's not, I look for some finite quotient of this group or use hyperbolic geometry or something. And in practice, that works. But on the other hand, maybe I would just give up. I mean, like we just don't encounter hard cases. There may well be hard cases. There's no reason to think that sort of primitively recursive. I mean, we don't know the complexity of the homeomorphism problem, and it might be quite difficult. In practice, it's not. But I don't know what that means.
Your manifold virtually fibered over a second.
Yes.
Can you tell me the index?
That you will typically run out of ability to find the cover. So I mean, so one thing Snappy can do is find covers. And one thing, in fact, in the most recent version we did was greatly improve its ability to find covers. So it can find covers much faster than before. I'm probably going to regret this. If you've never done it, it's really nerve-wracking to demo software that you're partially responsible for. Okay, well, all right, so there aren't very many covers of degree 7, degree 10, all the homology of all the degree 10 covers of this thing. So you can certainly enumerate covers up to some size using standard computational group theory things. And if you're lucky, one of those manifolds might fiber. Checking if something's fibered is also one of these things that's not hard in practice, but is maybe not so easy in theory. So for example, we have these censuses, databases of manifolds that come with Snappy. In most cases, we do know whether they fiber or not, but we don't use the algorithms. And there's always this tension between, there's the algorithm in the sort of theory literature that says, we'll give you the answer. That's not what you do in practice because it's unimplementable, or if it's implementable, it's slow. Instead, you use these heuristic tricks and they cover basically everything. And so what that means, I couldn't tell you.
I must make a follow-up question. So can you predict in practice the index by means of the volume?
No. Well, in general, for bounded, so like if you look at, say, Dane surgeries on the figure 8 knot, all of which have bounded volume, the degree you need to go to virtually fiber is arbitrarily large. So in general, volume is not somehow not going to tell you much about that index. There were some questions over there.
Is Snappy part of Sage or something separate?
It's something separate. So it's a separate thing. And if you just download the basic version off the Snappy website, it has nothing to do with Sage. However, when you run it inside of Sage, I mean, it's a Python-based program. If you run it inside of Sage, it gains extra features because it can use some of Sage's algebra and various other sub-components to do more interesting things. So it works both with and without Sage. So, well, sort of the standard algorithm involves, among other things, you look at, say, the SL2C representation variety. You're into the case where it's going to be hyperbolic, and you're trying to show this. The algorithm that finds a hyperbolic structure in theory is something like, you look at all representations to SL2C, you pull out the zero-dimensional components, you make those algebraic numbers, you start building a Dirichlet, trying to build a Dirichlet domain or just contribution discreteness. Any kind of thing that involves character varieties for a large manifold, the computer will just die. That's not what you do in practice. You do this sort of triangulation stuff in practice.
Connect the chalk part at the top, the computer part at the top. If you wanted to solve the homeomorphism problem in practice, what would you do?
So what you do is you find the hyperbolic structure by some technique which is not and then you compute something called the canonical cell decomposition. And that's something I'll talk about in the next lecture. Well, so I should say it's not well. Always means what do you mean by so there, for one thing, there are invariants, there are obstructions to fibering, Alexander polynomials, twisted Alexander polynomials. So first you apply those, and if it still looks like it might fiber, I should really say it's only in the cusp cases there really a good technique for finding the monodromy. Like if you actually want to show it fibers, but it's not so bad really. I mean, what you do, okay, you have a manifold. Let's say its first Betty number is 1, and you want to know, does this fiber over the circle, right? So build some surface that represents the homology class. Build a bunch of them. Take the simplest one you find, cut open along that. Now we have a manifold with 2 genus G boundary components. Does the fundamental group a surface group? Let me just look at it. Like look at the presentation. If it is, yes, it fibers. If not, go back and find some obstruction. This is not something like Snappy doesn't have this as a push button. This is like more sophisticated. But for example, in a paper with Stefan Friedel and Nicholas Jackson, like we determined which knots of 15 or fewer crossings fiber over the circle using these kind of methods. So that's hundreds of thousands of knots.
Like those bad cases that any surface generates the homology is exponentially large is not going to happen in practice.
Oh no, it can definitely happen. I mean, where it happens, yeah. Well, no, I mean it's true that the fibers can be pretty large. Yeah, it still works usually.
Question. So this thing that in practice it seems that the algorithms run fast, but in theory, the best known bounds are crazy. Is there any kind of refined bounds of the sort that if you can exclude something and then if you do, then you have good bounds or
yeah. So people have explored those kind of things in some cases. So there's sort of in the theory of algorithms, there's this thing called parametric complexity, where you like a good example in the context of 3 manifolds, let's say the bridge number of a knot. And so then you prove theorems like if the bridge number is fixed, then you can solve the problem in polynomial time and the number of crossings. Okay, now that's not this because of course, generally if you have a big pile of crossings, you have many bridges. But so if you keep that parameter fixed, then within that parameter, it becomes polynomial time solvable. The degree of that polynomial grows as the parameter grows. But then that sometimes can kind of give you some explanation of what's going on if the manifolds you encounter happen to have that parameter be small.
It's like problem solving session at 3:30.
And many of the problems involve pushing buttons.